Hello everybody. In this video we will learn about graphs of logarithmic functions. Okay, we know that if f is a one-to-one function, okay, we do have that is if f has a domain to be a and range to be b, and its inverse function f inverse will have the domain to be b and range to be a. Correct? So, and we also know that f of x is equal to a power x, where this is an exponential function with a not equal to 1, has domain to be R. Correct? So it is set of all real numbers, and range is 0 comma infinity. So what I said above, that what we learned till now, and exponential functions are one to one, therefore it has an inverse function, that is nothing but the logarithmic function that we learned in the previous video. So log x to base a is the inverse function with domain open interval 0 comma infinity and range R. So the graph, this means that the graph of f inverse of x is obtained by reflecting f of x in the line y is equal to x. This we learned while we were studying inverse functions. So since we know that log 1 to base a, or to any base for that matter, is always equal to 0, so this is nothing but the x-intercept. So the x-intercept is the x-intercept of y is equal to log x to base a is 1, and the y-axis is a vertical asymptote of the y-axis itself is the vertical asymptote of y is equal to log a x. So because as log x to a will tend to negative infinity as x tends to 0 plus. Okay, so there are many methods that we learned to graph a function. So all the methods apply here. So first is like graphing a logarithmic function by plotting points. So if we consider the function, say for example, if we consider the function f of x is equal to log x to base a, so now take arbitrary x values and calculate its log. But here you take the x values in terms of powers of 2. Okay, so okay, I will take a specific function here, say log 2 to x. So base is 2 here. So you take the input values to be like 2 cube, 2 square, 2 and 1 and 2 inverse, 2 1 over 2 square, or 2 to the power of negative 3. Okay, so the corresponding values will be 3 exponents only, 2 and 1, 0. Correct? And this would be negative 1, negative 2 and negative 3. Correct? If you now take the graph, okay, so the input values you need from 1, 2, 3, 4, 5, 6, 7, 8. Correct? And 1, negative 2. Negative values are not at all being considered because the domain is from open interval 0 to infinity, that is only the positive axis of x, and the y values will go up to 0, 1, 2, 3, 4. I have written one value wrong here, so this has to be 1. Okay, this is 1. Yeah, so now we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, for input value to be 8, output value is 2, correct? So the point is here. For the input value 4, output value is, oh sorry, I have to, for the input value 8, output value is 3, not 2. So the value will be here, the point will be here. And for 4 it is 2, correct? And for 2 it is 1. Fine. So then for 1 it is 0. So it is touching the x-axis. Then for negative 1 over 2. 1 over 2 is x-axis. 1 over 2 is somewhere half here. So that would be -1 here. And this will go on like this. Okay. So if you connect the points, the graph will look somewhat like this. Okay. So this is f of x is equal to log x to base 2. So this is one such method. And the other method is reflecting, like using different transformations and applying the table of values of the original graph. You have to choose a suitable original graph and apply all the transformation methods to the table of values of the original graph and plot it. Okay, so for example, if we have g of x is equal to negative log 2 to base x, so the above graph will be the original graph, and this is nothing but the reflection of it. So use the same table of values and multiply it by -1 for the functional values and plot it on the graph. You will get it to be a reflection. Okay, so and the same thing can be done even for shifting of graphs. That is, if you have g of x is equal to 2 plus log x to the base 2, see here you are obtaining g by from using the same above graph. That is, f of x is equal to log x to base 2 by shifting upwards for 2 units. So as shown here, like if you have, you have here, and shift every graph to 2 units, so you will get you will have the g of x graph to be somewhat like this, 2 units, right? So 1 1 2, so it will be somewhat like this. Okay, so this is our g of x. That is like shifting, applying the transformation of shifting the functional values upwards by 2 units, correct? And you can do the same for input values also. So if you are given to plot h of x is equal to log 2 of x minus 3, so in this case you have the same value, but what you are doing is you are obtaining g by shifting to the right of 3 units, shifting the original graph to the right of 3 units. So this graph, that is h graph, h will look like 1 2 3, so it will look somewhat like this, the one that I am drawing in the blue line. So every possible method of graphing that you learned in all the previous sections can be applied in this for these functions as well. But for the original graph, the asymptote will be always y-axis itself. But here for h, the graph h that I have drawn in blue, the asymptote will be x is equal to 3. So this line x is equal to 3 is the vertical asymptote, and the vertical and the horizontal asymptotes changes as you apply the transformations of shifting, stretching, shrinking, or any other methods that you apply for solving the or plotting the graphs. So now it's time for quiz. I'm sorry, quiz 4.3.2. Do number 50, 62, and 64. Okay, so this is basically of graphing the given problems. So applying all the methods that I taught you now. In the next video, we will learn about common logarithms and natural logarithms. So common logarithms are to the base 10 and natural logarithm is to the base e. Okay, the irrational number e. We will learn more about them, like how to evaluate them and how to apply it on the for real world problems, as well as how do the graphs look like, and also drawing graphs for both of the things, and to find domain and range, and analyzing certain properties of the graphs. So see you soon with the common